In addition to vertical asymptotes, rational functions also have something called horizontal or oblique asymptotes. So a horizontal asymptote, which we can abbreviate HA, right? The horizontal line, and if it's horizontal, it has the equation y equals some constant. We'll use a big L like the book. Is a horizontal asymptote of a rational function if that rational function approaches that line as x approaches infinity or x approaches negative infinity. It's important to note that a rational function might cross its horizontal asymptote. And so anytime you find a horizontal asymptote for a function, you must find if and where it crosses. You might say, why can it not cross its vertical asymptote, but it can cross its horizontal asymptote? Well, let's look at a couple of pictures of horizontal asymptotes, and maybe that will shed some light. So here is a horizontal asymptote right here with equation, equation y equals L. Okay, so this is crossing here at L. Okay. And let's say we had some kind of a rational function that looks like this, and there are some that look like this. This one doesn't have a vertical asymptote, not everyone does. And we can look at either end and say, oh, it looks like r of x is getting closer and closer to L, right? As x is getting smaller and smaller, so going to negative infinity. And we can look here and say r of x is also going towards L as x is going closer and closer to positive infinity, right? So that one doesn't cross, that function doesn't cross its horizontal asymptote, but this one is going to. So here's a rational function with, let's call this a vertical asymptote, and we'll say that this is the horizontal asymptote, y equals L, so this is going through L. Okay. You might have a function that looks like this. It's going to approach its vertical asymptote and approach its horizontal asymptote, but never cross it here. It's going to approach its vertical asymptote here, but it's going to cross and maybe cross again, and then approach L. So notice our function here is crossing the horizontal asymptote in two different places. So r of x crosses the horizontal asymptote. Well, it's allowed because we can still fit the definition that says over here r of x is approaching L as x goes to infinity, and over here r of x is approaching L as x goes to negative infinity. So when we're thinking about horizontal asymptotes, we don't care what's happening in the middle of the function near the origin. We really care about what's happening here at the two ends, right? All that has to happen is that the two ends have to approach the line y equals L, not anything in the middle. And it's still considered a horizontal asymptote by definition. Okay, so we have horizontal asymptotes, and another kind of asymptote that a rational function can have is called an oblique asymptote. Sometimes these are also called slant asymptotes, but your book uses oblique asymptotes. If we have a rational function, r of x, and it's approaching, instead of some horizontal line or y value, instead it approaches a line. Notice that I've written it in the slope-intercept form, where the m, or the slope, is not 0, right? Because if the slope were 0, that would be a horizontal asymptote. So I'm talking about a line that's, what we might consider slanted. which is what we call slant asymptote. If that happens as x gets larger and larger to infinity, or x goes smaller and smaller to negative infinity, then we call that line, we call the line y equals mx plus b an oblique asymptote of r of x. Okay? Now, something else important to note. A rational function may only have a horizontal asymptote or or an oblique asymptote, but not both. And maybe it will have neither. Okay? All right? But if it has one, it will not have the other. Why, if it has a horizontal asymptote, can it not have an oblique asymptote and vice versa? Well, remember what we're doing. We're looking at what's happening as x approaches infinity. It can only be doing one thing, right? As x gets bigger and bigger and bigger, what is the value of the function doing? As x gets smaller and smaller and smaller, what is it doing? It can't approach two different values, two different lines. Okay. Here's a picture of an oblique asymptote. We're going to draw a vertical asymptote here, and then we'll also draw an oblique asymptote, like I said, maybe at a slant, maybe like this. Okay, and this is the equation of this is y equals mx plus b. We can see that it has a negative slope because it's decreasing from left to right. Okay, your rational function might look something like this. It might come down this way. And you might say, oh look, it's approaching its vertical asymptote here, right? As as x gets closer and closer to that value. But here at the end, right, the function itself is approaching the line y equals mx plus b as x goes to negative infinity. And the same thing could possibly happen, you know, down here. But either way, that function is really approaching a slanted line instead of a horizontal line. So we call it an oblique asymptote. Okay, I'm going to give you some rules for horizontal asymptotes and oblique asymptotes. I think the way the book lays it out is a little confusing, and I think I can do it a little bit more simply. Okay, so the first rule is that if the degree of the numerator is larger than the degree of the denominator, remember both the numerator and the denominator of a rational function are polynomials, so they have degrees. So if that's true, then there is no horizontal asymptote. You might say, why? Well, I'm going to show you. Okay, but first let's write down the rules. Okay, number 2. If the degree of the numerator is equal to 1 more than the degree of the denominator, right, then there is an oblique asymptote, okay, and then you have to find it, okay. Number 3 says, and I'll show you how to do that too, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is always the line y equals 0, or the x-axis. And the 4th rule is that if the two degrees are the same for the numerator and the denominator, right, then the horizontal asymptote is the ratio I'm sorry, that's not how I want to say it, is y equals the ratio of the leading coefficients of the numerator and the denominator. Okay? Alright, so those are kind of rules that you could memorize. You'll get pretty used to them after you're working with the functions, and you might start to understand why, and then memorization becomes a little bit easier. So why do these work? I'm going to do a few examples for you. of finding horizontal and oblique asymptotes, and you'll see why these rules end up working. Okay, so the first example that I want to do is we're going to find the horizontal asymptote or the oblique asymptote of r of x equaling 3x to the fourth minus x squared all over x cubed minus x squared plus 1. Okay, now according to the rules I have up here, it says, number 1, if the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. So notice I have the 4 is bigger than the 3, those are the degrees. So I see that there is no horizontal asymptote. The second one, though, says that if the degree of the numerator is exactly 1 more than the degree of the denominator, then there's an oblique asymptote. So 4 up here is exactly 1 more than 3, so then there is an oblique asymptote. Okay? So now what I'm going to do is show you how to find an oblique asymptote. So to find an oblique asymptote, you use polynomial long division. I might run out of time in this video to do the whole example. I'll just pick it up in the next one. Alright, so we're going to divide the denominator into the numerator because that is what the function is. Oh, excuse me. I forgot something. When you do polynomial long division, you want to make sure that you add in, or at least that's the easiest way, to add in missing degrees. So here I have a 4th degree term. I'm going to add 0 as my 3rd degree term. The 2nd degree term is already there, plus 0x plus 0. Right, so now they're still equivalent, I just have some more terms to work with. I'm going to say how many times does x cubed go into 3x to the 4th? What do I multiply by x cubed to get 3x to the 4th? That's 3x. Now I multiply it. I take 3x times x cubed is x cubed is 3x to the 4th. 3x times negative x squared is minus 3x cubed. 3x times 0x is plus 0x squared. 3x times 1 is 3x. Now, just like regular long division, we're going to subtract these. The first terms cancel. 0 plus, notice it's a minus, 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 so plus, so I get 3x cubed. This one becomes a minus, so minus x squared minus 0 is minus x squared. 0 minus 3x is minus 3x. Okay, and then I bring down the plus 0. Continuing, I'm going to now take x cubed and divide it into 3x cubed. Well, that goes 3 times, because 3 times x cubed is 3x cubed. 3 times minus x squared is minus 3x squared. 3 times 0x is 0x. And 3 times 1 is 3. Then I'm going to subtract this entire thing. The first term, of course, cancels. Minus x squared minus minus, so that's going to be plus 3x squared. That's 2x squared. Negative 3x plus 0x is negative 3x, and 0 minus 3 is a negative 3. Okay, now I'm going to stop there because there's nothing left to bring down. So my original rational function said 3x to the 4th minus x squared over or divided by x cubed minus x squared plus 1. Now when I actually carried out the division, I can now write my function as the quotient plus the remainder over the divisor, right? This is the remainder, this is the divisor, and this is the quotient. Okay? It's still equal to r of x because it's just division written in a different way. Okay? Now, next thing we're going to do is we're going to say, okay, so what happens when x gets really, really big? What happens to r of x as x goes to infinity? And what happens to r of x as x goes to negative infinity? Okay? Because that's what part of our definition of the oblique asymptote is. Okay? Next video.